wasn't it?
It will be when I push play.
Yeah, you're
Paul, nice to see you.
Yeah, good to see you too.
Good.
Yeah, so you're here in a sort of master of ceremonies type.
That sort of thing, yeah. Okay, could we make a start? Crikey, it works, this microphone, doesn't it? Very warm welcome to you all, particularly warm welcome to our industrial visitors today for our annual research showcase. I'm particularly pleased to see so many people here. Just looked out the window this morning and thought, oh my God, we're going to be talking to ourselves here, but I'm very pleased to see we're not. The format is there are 3 talks from the department in the next hour, and then we'll have a break, and then we'll have the main speaker, Nick Molden. So our first speaker, as you can see up here, is Fred Segler from the NDE group. So Fred, over to you.
Okay. Can you hear me? Right, great, good. My title is Structures We Have Ways of Making You Talk, and I thought after I came up with this title, I've heard it in the pub often before, and you probably can hear a hint in my that I have an accent myself. I thought I'd better find out where this actually comes from. So I did a bit of Googling, and I found out that the first mention of this phrase, "we have ways of making you talk," comes from a 1935 movie by Gary Cooper, The Lives of a Bengal Lancer. And the scene is shown on the right-hand side here. Effectively, it involves burning bamboo splinters being pushed underneath fingernails. And I think at that point, you'll be happy to know that in NDE, my specialty, we try to do it without the torture. It's really non-destructive evaluation. That's what we try to do. The biggest part of that is really visual and optical, looking at surfaces. But if you want to look beneath the surface, then you use more advanced techniques, things like X-rays, electromagnetic and ultrasonic investigations. And since I'm based in the mechanical engineering department, I really focus mainly on ultrasonics, a little bit of electromagnetics, looking at mechanical waves to probe beneath surfaces, probe structures. And so rather than giving you a long list of research stuff that's currently happening, I thought I'd do it a bit personally. I'll tell you how I got into the field, what I currently do, and then at the end I'll tell you a little bit about the current research that's going on. So it all started for me with doing a PhD on fluid characterization using guided waves. And what we were looking at were fluids like ketchup, mayonnaise, honey, Nutella, motor oils, things like that. And what we really tried to do is have a transducer at one end of a waveguide. Could be something very robust and small, something like a metal strip, and send a wave along that and dip it into a liquid, and then by the changes of the wave properties work out what the type of fluid properties are. And I focused on a particular type of wave mode. So that has been done quite a bit with leakage of waves, where energy is getting lost out of the waveguide. But I worked on a wave that was called a Shorty Wave. That's an interface wave. That's something where energy is trapped at the liquid-fluid boundary and propagates along the waveguide, and you can use that to analyze what's in the fluid. And that was quite successful. We could do all sorts of things. Just to show you some examples, we could evaluate the bulk velocity, so that's the wave velocity in the fluid, as a function of temperature for different fluids, so distilled water, for example, measurements versus literature values, a 5% distilled water ethanol, a 5% ethanol distilled water mixture, that also worked really reasonably well. And at that time, I used to go to the pub late in the night, and I sometimes also measured the fluids that we found there. So I came back and measured some beer, and you will be pleased to know that also fitted into that. So I could show you quite a lot more slides. We did a lot of work on also scattering of particles in the liquid and evaluating the liquid properties with the particles in it. But to cut the long story short, there wasn't really that much interest in industrially taking up these measurement methods. Even though they were great, I got quite a few papers out of it. And what happened next was, bam, a big sort of event outside. This is 2005, the Texas City Refinery Explosion and fire in this, and this is one of the biggest refineries in the world, and it was owned by BP at the time. I think it might still be. And basically that's the aftermath. The whole plant was shut down, and at a huge cost, and the company was looking into better technology of surveilling their plants. So what we then, and usually when you do inspections in these plants, you have to shut down the plant because it's hot while it's operating, and conventional ultrasonic technology usually works at room temperatures or a little bit higher. So really talking to representatives coming around, they were actively looking for technology. We thought we could use the same sort of principle that we used for the fluid measurements, where we separated out the transducer, which is fragile, and also electronics to process all the data from the hot environment, the specimen that we would want to look at, and here mainly we're looking for corrosion damage or wall thinning, and by means of a thin waveguide, something like a metal rod of this sort. And if you very quickly do sort of a heat transfer analysis, if you think that one end is at a 500 degrees constant temperature, and it's surrounded by air, ambient temperatures, for thin and slender waveguides, such as this one here, over a distance of about 200 millimeters, so this much, it cools down from the 500 degrees just by natural convection to something below 100 temperatures, where you can use all conventional ultrasonic techniques and attach lenses. So that was very encouraging. And then we looked into doing this. So in the lab, I knocked up some transducers simply by attaching them, clamping them on at one end, and also designing clamps at the other end to basically just dry couple them on, bolt them onto the specimens. And we always use two transducers separators, in parallel separators, so you can see that better in this slide here, where you have one waveguide sending a wave and the other one receiving the waves. And the nice thing is that that always gives you a reference signal via the surface, and then also some waves that bounce off the back wall, that's what you're saying. So I could very quickly show in the lab that you can make that on a step plate of different thicknesses. You receive these sort of ultrasonic signals, a reference reflection at the front, and then signals that arrive later and later as the plate gets thicker and thicker. And just by measuring the travel time, you could very simply measure the wall thickness. I was also quite good in the lab making these things relatively. It's a really strip of stainless steel with a transducer attached to it, so it's relatively simple. And we had, oops, got to press here. And as I said, we had the backing of BP, who were interested in installing these things in their plant. So we were able to develop this, a full wireless sensor that contained all the wireless head, which has a battery, electronics card, a wireless send-receive module, and also the transducers. And we could attach that to the top of the waveguide, launch a wave into the material, have a simple clamp that is bolted on via stud welds onto the pipe material, and then these waves bounce up and down in the pipe wall, and we can measure the travel time between and measure the thickness of the component. No, it was really great to also try this out in plants, and we could show that it's really robust and reliable. So here this is a thickness measurement over the period of 3.5 years. But you can see nothing much is happening, but we're continuously getting the data out. In other locations, we could see that there's quite a bit of thickness change over a shorter period of time. So we're actually measuring real stuff that's going on in the plant. And just to demonstrate the advantage over the status quo at the time, that was if you do manual measurements, usually you have to shut down the plant, and or just getting there was difficult. So the most frequent you could do this at about 6 monthly intervals or so. And also if an operator goes out there, there's all sorts of coupling errors associated. Are they really in the same spot? Are they coupling the probe? Is it set up in the same way? And usually it's sort of an uncertainty of about half a millimeter. And there, so if you want to then look at trends, well, is it going downwards or upwards through here? it's a bit difficult to tell. But if you look at sort of automatically monitored data, then you can clearly see you get a lot more information. You can clearly see 3 regimes here, some corrosion happening, nothing in this period, and something happening there. This gives you, you can then correlate this type of data with your process that's going on, and you can take concrete actions coming out of this. And again, I think that was the success of the technology. For example, this is a real example from a refinery. This is a sensor installed at the overhead pipe coming out of a crude distillation unit. So the distillation unit, the pipe at the top where the distillate comes out. And there's a big problem that often there's condensation. And when condensation occurs, also some corrosive species fall out, and you get corrosion on the pipe walls. And that's well known, so people inject inhibitors into their processes. But in this particular case, well, they got it wrong. And there was quite a bit of corrosion, so over a period of a month, 0.5 millimeter wall loss. So based on the data that they monitored, they could go back, tune their corrosion mitigation strategy, optimize the dosage of inhibitor they're injecting, and basically rectify the problem. Another example is somewhere from a plant by the sea. So this is, you can see, again, wall thickness monitored, again a overhead pipe in a crude distillation unit. And so there you can see sort of monthly intervals, there's different corrosion behavior. And this has to do with effectively different feedstock arriving at the refinery. You can correlate this back to it. And depending on where the feedstock comes from, it can have more or less corrosive substances in it, depending whether the tanker comes from somewhere in Africa or Saudi Arabia or wherever. And then you can judge and make a call on which feedstock is best for your refining process to elongate the life of your plant. So this was really quite successful. We set this up as a spin-out company out of our lab called Permasense Limited, and they sold the full system, the sensor, the wireless acquisition equipment, associated also the data processing, and so that you could look at the data to desks, really. And to date, it's been installed in over 180 plants worldwide, more than 17,000 sensors, done on more than 20 million measurements. And since 2016, the company has been acquired by Emerson and integrated in a bigger, what do you call it, monitoring sort of environment for the oil and gas industry. So I think this shows you a little bit how I got into my current research area of using NDE to monitor assets for structural integrity or plant integrity. And the sort of recurring story is that, you know, you would look at it, if someone sold you a plant, you would see a shiny picture of the plant being all nice and looking rosy. But if you look underneath it in real life, there's always degradation taking place. And this is really what you would see on the inside. There's always a process, degradation processes that are continuously going on, whether that's corrosion, cracking, or any type of other degradation process. And so what we really try to do, and this leads into sort of the work I'm doing in general, is we try to surveil these plants and try to make sure that there's no critical damage in them. And ideally what you want to know is you would want to know everything in space, spatially dense mapping, and you would also have temporally dense information. And that's really the holy grail of structural surveillance, where you would want to be. However, in real life, that's very hard to achieve or uneconomical to achieve. So there's conventional technology for surveilling, for, in this case, corrosion damage, for example, where you can have robotic scanners to get over your plant. You get very spatially dense information, but you don't do that very irregularly. So you have only very infrequent data available to you. Then there's the other example that I've already shown you, the monitoring example, where you had one spot location and you can get very frequent data. And if you want to go up to this corner here, we always need to strike some sort of realistic trade-off in between, and that's really what we're working on, is getting towards that from both sides, from the spot measurement and frequently monitoring side, and also extending coverage and making monitoring and making scanning and full coverage inspections better. I'll show you some examples, recent examples of projects that we had. So, for example, a better use of data, making use of the sparse monitored data more frequently, or the sparsely scanned data more frequently, is by means of where we have some data on a structure available, say this for this green area, but we want to assess the overall structure for data, so that we can create a statistical model from this data that we have, and then try to extrapolate out what the worst case condition in the structure is. And we can do that by quite a bit of modeling, also taking into account the transducers and the data that comes back, and using something called extreme value analysis, so for NDE data. And my PhD student Daniel Benstock recently completed a thesis on doing that, and how to handle this. Then another thing I work on is sensors. So here, really trying to, we have large structures, and we're trying to basically make sensors as cheap as possible and as robust as possible to get the most reliable data. And there's all sorts of boundary conditions also, that they need to fit into hazardous environments. They need to be low power, because often they're battery powered or they're autonomous, and they need to have some connectivity. So the type of sensors, I've recently worked quite a lot on are electromagnetic acoustic transducers, and they're a very nice thing. They're non-contact effectively, or you need to be in close proximity, and they work by magnetically, if you have a specimen, a metal or conductive specimen, you bring a coil next to them, then they induce an eddy current in the surface, and if you place that into a magnetic field, a bias magnetic field, then that launches a wave out into the material. And the nice thing about this is that you can just reshape the coil or the magnet easily to get a different ultrasonic field and optimize them for different inspections. The disadvantage is that they're very insensitive, and so hence we need better equipment to talk to them and to exploit them. And again, we've done quite some, I think, good work with my PhD student Julio Isla, who's really worked on optimizing the magnetic fields of these types of transducers by being able to increase the bias fields, and clever design of the transducers. He's been able to show that we can get 20 dB increase in signal-to-noise ratios. And similarly, we've done quite a bit of work on coded excitation, so sending out signals that are encoded in a certain way. And using this type of technology, we are also able to show that we can, with the same power levels, we can get 20 dB increase in signal-to-noise ratio. Something I'm really excited about these coded sequences about this is also that it enables you to send simultaneously on many transducers. Where in NDE, usually, what you do is you send on one transducer, receive the data on all other transducers if you have an array, if you want to form an image, for example. So you would do that, send on the next one, receive that. With our coded approach, we can fire simultaneously on all of the transducers, get the data back, and unscramble what comes back from it. And so we have also recently shown for the first time that it's possible in a medical array probe, where we build a custom-made array controller, and we looked at wire targets from this array and spring targets, and we were able to show that we could get images using this coded sequences approach, where we simultaneously fire on things. Lastly, I want to show you a sort of slightly different look at this, and that's really looking at a grant we've been involved in as part of the ORCA offshore robotics hub, and that's really making the manipulation of NDE probes easier and make it possible via robotics systems. So this is a large consortium led by Heriot-Watt University in Edinburgh, and we're part of it. The Imperial Aeronautics Department is part of, as well as with Dr. Mirko Kovac, and what we're trying to do is really deploy NDE sensors robotically remotely. And I'll show you some early results from this. So here you have Basically, this is in the drone lab on level 5. We have a drone basically delivering, just with manual pilot, a EMAT sensor that's permanently installable. So this is just a magnetically attachable sensor that you fly on with a drone. And we can also do this on things like, oops, something gone wrong with the video, but you can also do this on pipe-like structures. So you can see this here with the sensor being deployed with a drone on a pipe. All right, so this brings me to conclusion. I think I've shown you the research I do is based on NDE methods for asset integrity assessment. From my point of view, key drivers to make this successful is to have cost-effective, reliable data acquisition, short response time from the acquisition of the data to making a decision, and making it really practical in the field to collect data. And the current research is really on extending coverage of sensing techniques and the data analysis, better sensor and acquisition technology, and we're integrating this onto robotic systems. So I would like to acknowledge all my colleagues in the NDE group, the RCNDE, who is a big network of research in non-destructive evaluation, all the students and postdocs and staff that I've worked with, and of course the sponsors. So thank you for your attention.
Time for a quick question if anyone has. No question. Okay, Fred, thank you. Our next speaker is Liliang Wang from our Mechanics and Materials group, who will talk about metal forming. Yes. Liliang.
Hello? Can you hear me? Okay. Good afternoon, everyone. My name is Liliang. It's my great pleasure here today to see you all, especially in such a cold weather. So warm welcome. And also it's my great honor here to present my research in front of you. The title of my presentation today is Cloud FE Simulation of Metal Forming Processes. For those who are not very familiar with metal forming processes, I would like to take 1 or 2 minutes to give you a brief introduction about the keywords that I'm going to talk about today. So what is metal forming? Metal forming technologies are actually using a tool or die to shape a piece of metal into final products. If the raw material being used is a piece of bulk metal, then the forming technology is usually called forging or bulk metal forming. If the raw material is a piece of sheet metal and the final product is a thin-walled structured panel component, then the forming technology is called stamping or sheet metal forming. The metal forming technologies have been used for many, many years. Since 7,000 years ago, people start to develop metal forming technologies and use them to manufacture tools or weapons. And now the metal forming industry has grown to a huge industrial sector which produces over 1.5 billion tons of steel and over 53 million tons of aluminum every year. This raw material will go into different sectors, industrial sectors, to be manufactured into final products that can be used every day. And among them, over 90% of the products was actually manufactured by using metal forming technologies. Since metal forming technologies are so important, is creating such huge impact, we can find applications of the products everywhere in our daily life. For example, in our buildings, in the beverage cans, in aerospace industry, aeronautics industry, and also in the automotive industry. When we are talking about the automotive industry, the direct impression is the high volume production. Every year, millions and millions of cars, passenger cars, are being manufactured. In the year 2015, for example, over 89 million passenger cars are produced globally. And this value will be increased to over 113 million in the year 2025. If we are talking about the sheet metal forming products alone for the automobile applications, the market size is over 93 billion British pounds in the year 2015, and this value will be increased to 115 billion pounds in the year 2025. If I finish my presentation today in about 15 or 20 minutes, the panel components being produced by sheet metal forming technologies will worth over 4 million British pounds. I'm sure most of you are very familiar with the finite element simulations already, but I would like to go through the history briefly. In early 1940s, FE simulation was for the first time being applied into civil engineering problems or aeronautical problems to do static analysis of the structural strengths. And in the late 1960s, for the first time, FE simulation was applied into metal forming process to predict the defect in the forging process. And now, FE simulation is becoming more and more important. Just imagine a designer in the automotive industry. They will not be willing to sign off a die-making contract if they don't see a robust FE simulation result. So FE simulation is becoming more and more important in this industry. It's becoming more accurate and more efficient. So if we would like to achieve more efficient and more accurate FE simulation in the future, what are we going to do? We think the next step will be the cloud FE simulation. There are clearly three major benefits out of the cloud FE simulation. The first one, since our FE simulation is being operated online in a cloud environment, so it will enable the metal forming engineers to share their knowledge easily. And then, in order to improve the efficiency, we will use the multi-objective simulations instead of the conventional user subroutines to achieve more efficient FE simulations. And the third one, since we share our knowledge and we will collect a lot of data during the cloud FEA, but using this data, this will enable a high-value strategic manufacturing process. And I will talk about the details in my following slides. First of all, I would like to acknowledge my group members who are sitting in the middle of the room. And here is the picture. The old man standing in the middle is me. And all the other group members are very young. They are very energetic. They were born after 1990s. They feel a great passion for doing research. And every day, they have some keywords in their mind in these young people. One of the keywords is to do cool stuff. They would like to do cool research, and they would like to share their happy moment online, maybe on Facebook. They would like to share their delicious food on Instagram. They use WeChat, they use Twitter. When they come back to the college, they will have to do research. Unfortunately for research, the only way for sharing their knowledge at the moment is journal papers or conference papers. This is difficult, and also for engineers, if they would like to understand the novel technology or new theories, it will take some time, and it's quite difficult for them. Therefore, an easily accessible knowledge center does not exist at the moment. So this is the motivations, one of the motivations for us to develop the cloud FE simulation technique, which will enable the metal forming engineers to share their knowledge, making their knowledge easily accessible and create direct impact in the industry. And now I'm coming to the second topic, which is the multi-objective simulation. And thanks to my group members who develop individual functional modules, and they are willing to share online. We developed many functional modules, including FLD, tool life, etc. I will briefly go through them one by one. FLD is actually called forming limit diagram, which is a very important concept in the sheet metal forming industry to predict the failure of the sheet components during the forming process. Conventionally, people using thinning or deformation or plastic string to estimate or to predict whether failure will take place or not. In our forming test, we checked the simulation results against forming test results. We found that the most thinning is taking place in the corner regions. What happens in the experiments? In the real experiments, we found that thinning is not taking place in the corner regions, but instead it's taking place on the side wall. For different aluminum alloys, we conducted a test and we found the same results. In order to predict this or represent this feature, we developed new theory originated from Professor Lin's pioneering work. So this is the viscoplastic material model, which is not only able to predict the evolution of flow stress against the different temperatures, but also strain rates. More importantly, we are able to represent the complex response of the material at a changing temperature and changing strain rate. And then we need to predict the forming limit diagram, and we integrate the MK model into the constitutive equation. As you can see, the typical V-shaped curves can be accurately predicted. And also, not only at constant forming speed or constant temperatures, we are able to predict the evolution of forming limit diagrams against different speed and the different temperatures. The comparison has indicated that we reached a very good agreement between the experiments and the forming limit prediction, which shows that the failure is taking place on the sidewall. If we compare the conventional or traditional idea to predict the forming limit by using thinning, we can see that in region 1 and region 2, they are showing similar thinning values, but if you compare the failure values, it's very different. And another powerful functional module is the tool life. We are using FE simulations to simulate metal forming processes, but unfortunately, most people are running one single loading condition FE simulation. For metal forming tool, I wouldn't be surprised to hear that the cost of the tool is over 1 million British pounds. So we will never use a tool to form just one component at a time, which is too costly. So in the Euro case, it's a multi-cycle loading condition. So that's the idea how we developed this functional module. But before predicting the tool life and the multi-cycle loading conditions, we need some new models. So we collaborate with our nice colleague in the tribology group, Tom, and we develop a new model, which is called the interactive friction model. In the lab scale testing, we found that the evolution of the friction coefficient follows this style. So at the very beginning, friction coefficient was pretty low and stable. This is because of the effects of the coating. But when the coating starts to break down, the friction coefficient suddenly jumped up to a very high value. Obviously, we don't want to see that in the real forming process. And in order to predict that and capture this feature, we developed a new model, which is a combination between friction and wear. We think these two phenomena are interactively affecting each other. So we developed a new friction model, which is called interactive friction model. And we are able to capture the feature of friction coefficient evolutions during the lab scale testing. We can see that the x-axis is the sliding distance and the y-axis is the coefficient of friction. So if we increase the load, the coating life will be shortened. And we implemented the new friction model into our FE simulation in order to guide our daily production. This is a very simple U-shaped forming, and we can see that under different blank holding forces and different forming cycles, the tool life becomes different. Of course, if we increase the blank holding force, the tool life will be shorter. And also, we are able to predict the evolution of the residual coating thickness against the different forming cycles. And this is a unique and interesting functional module. And another functional module I would like to talk about is the tool maker. So we're not only focusing on theoretical development, but also small testing rigs. Xiao Chuan is responsible for the development of this novel IHTC Mate testing rig. This rig is being able to integrate it into global system, and then we are able to capture the evolution of contact pressure during a metal forming process to determine the interfacial heat transfer coefficient for hot stamping process, which was invented by Professor Lin. And as you know that during the metal forming process, the contact pressure will never be constant. So we test the material at a variable or changing contact pressure in order to reduce the number of testing. we are able to precisely determine the evolution of IHTC values against the contact pressure. And then we develop advanced models and then implement it into FE simulation. We are able to optimize the processing parameters during the hot stamping process. Obviously, if we apply a very low contact pressure or blunt holding force or contact force, some of the materials will not be well quenched. But if we optimize the processing parameter, we will ensure that everywhere in the components can be quenched properly. And we are also able to predict the post-form strengths afterwards. And the next functional module is Tailor. We believe that for each single aluminum component being formed during a hot stamping process, and the forming processing parameters should be unique. And the evolution of the post-form hardness is a very tricky phenomena, because if we really want to predict the post-form hardness, we really need to consider two important factors. One is the residual dislocations, which is left after forming, and the other one is the chemical composition of your alloys. So we develop a new model and implement it into the FE simulation, and we are able to predict the evolution of the post-form strengths in real components. And the last one is a uniform, which is actually developed by a group of DMT students, supervised by myself and the PhD students. The idea is to represent the conditions we applied in Tailor and then verify in the real world whether our prediction is correct or not. So we use a very fast heater at the very front of this rig, enabling us to heat up the blank at 200 degrees per second. And then we form the part by using a cold die. And this chamber is very interesting. So we are using this to simulate the real production. In the automotive industry, we have the multi-cycle paint-bake process. So this temperature change is simulating the real world and then simulating the multi-cycle paint-bake cycles. And then we already share our knowledge. We also enabled the multi-objective FE simulations. Now we will talk about the third one, which is the high-value strategic manufacturing. Since we have already collected some data globally, and we think that we could apply or implement this data to promote new research, new technology, and then new business, which is the high-value strategic manufacturing. In the past 5 or 6 years, we established the collaborations with our research partners globally. And when we explain our idea to share knowledge, all the researchers are very excited, and they are very willing to share their FE models, their advanced models, their techniques with us. We are now collecting different FE models from different colleagues in the world. And in the meanwhile, when we run these FE simulations, data will be collected. With this data, how can we use them? Maybe the data will provide us a completely different angle to view a metal forming process. Previously, we think we are expert, we think we understand the metal forming technologies very well, but the data will provide you a new insight to review the metal forming technology again. It provides you all the details into a metal forming technology. For example, how to do friction test. Previously, we're using a constant load and running a long distance friction test. But actually, in the real metal forming process, contact pressure is dynamic, it's changing all the time. Temperature, sliding distance, everything is changing. So how do we apply this condition into our friction test? We need to follow a data-driven testing approach. And then after we running our test, some new testing results will be obtained, which will force or push us to develop a new model or new series to be able to represent these results or explain these results. We're not only reviewing metal forming processes in a static way, but we are able to review the metal forming process, its digital characteristics in a dynamic way. And also in our friction test, for example, we need to apply a changing conditions. For example, the load is changing. At the very beginning, the load is very low and followed by a sudden jump in the contact pressure. And that does influence the friction coefficient. And we need to also produce or propose a new model to capture that, being able to predict this. So this will be very interesting as well. So for this one, this is another review of the data for existing metal forming technology. And this can be used to guide us to do material testing. Since we have the data already and we understand the users in more detail, so we need to develop new forming technologies to be tailored to each individual customer. For example, we developed a fast light alloy stamping technology. The patent has been filed. So previously, this is the conventional hot stamping technology. The principle of the technology is to enable the change in microstructures. So we heat up the material to the solutionized temperature or austenization temperature, and then soak the material. By using cold die forming and quenching together, we will trigger another phase transformation, change the microstructure into martensite. But if we can do this quickly enough, probably we can finish that within a very short period of time. We can increase the ductility to enable very complicated geometry components to be formed, but in the meanwhile, we can ensure that the post-form strength is very good. And this technology can be not only used for ultra-high strength steels, but also for different light alloys. With the data, I think we can also create a new business, for example, the high-value strategic manufacturing. Industry 4.0 is a very popular concept now. Actually, people are implementing sensors in different factories or plants so that they can talk to each other. For example, we will predict that the forming process is not going to succeed in one plant because of the failure of the tool. Then we can transfer the forming process to another plant. But actually, there is no efficient way to link all different industrial sectors together. So that's why metal forming process plant is become very isolated, expensive, and low efficiency. With the help of cloud FE simulation, we are able to link different industrial sectors together. So we understand the needs better than other people. So this will enable the UK to run the high-value strategic manufacturing. That's all. Thank you. Thank you for your attention.
Okay, I think in the interest of time, we'd better move on. Thank you, Lily. Obviously, speakers will be available in the tea break afterwards. Our third and final speaker in this session is Yanis Hardaloupas from the Fluids Group. Yanis.
Energy applications and air quality, partly because of the main speaker today, and also look at aero engines and car engines and combustion, because this is a recent and very popular subject of discussion. And in order to look at those, we use laser techniques, which we develop and apply, and also we develop sensors which can be used actually to monitor the emissions and control the emissions. And I'm around for 30 years now. I have done my PhD here, so I'm not going to start from my PhD thesis, but I will focus more on the... why lasers? Lasers are non-invasive. You probably all know about the application for surgery. So we are using them exactly for the same reason. They are non-invasive, and what we do is sampling eventually the flow without disturbing it. It is always important, and that's what you enjoy when you do experiments, to be able to see what is going on. And you want basically to measure everything, and if somebody comes with any quantity apart from those that I have on the screen, we will try to find a way to actually measure it. It is hard, and I want also to make sure that everybody who gets involved understands that it is not an easy thing to do. You have to understand the maths so that you can talk with the computational colleagues. You have to understand why you want to measure it, and eventually understand the lasers and the optics, so going towards physics in order to be able to do that. You should have the ability to program a computer, because you have to make the instrument to work. And eventually, and that is a bias, I do believe that the person has to be an engineer, partly because an engineer has the strength of character to keep going when really things do not work. And that is common. My first application is on aero engines and gas turbine combustors. And as I said, it is important to see things. We do have this combustor that you see, which is optical. So this section of the combustor, which is about half a meter, is optical. And I will show a video which has also sound. And as a consequence, I will go outside and run it, because, as I said earlier, it is important to actually see and also hear what is going on. So this is the combustor that it is operating, and you have a full optical access inside. It is very noisy because you do have combustion oscillations, which is a big problem. And at this moment there was a switch, the flame changed completely, it became quieter, and you see that this has happened several times while we are talking, and that changes the level of noise, so the acoustic signal, and as well the behavior of the flame. And this is important to be able to control and ensure that eventually this does not happen, because the pressure signal that you see here, so during the time that the flame changed and it became quieter, that is the pressure signal, while in the other cases you do have much higher pressure oscillations. This can destroy the combustor, and you want to avoid it. So if we want to look inside the combustor, that's why it is optical, and you want to be able to do that by measuring the velocity field, and that is time-dependent velocity measurements using particle image velocimeter, so illuminating with laser inside the combustor. And what you see down here is also the flame, how it behaves, which is excited now with a different laser, so you track OH radicals that are generated in the reaction. And you want to try to link the two, and basically when you have a minimum signal and a maximum pressure signal, you see that the flame is completely different, and you want to see how this matches with the velocity. And it becomes easier to see that by filtering out some of the noisy part that existed in the previous signal image, and the red part is a flow which is reversing and goes towards the nozzle exit, and all the red part is a recirculation zone which actually modifies the flame, and you need to see how this behaves, which also explains how the flame behaves. we have used what we learned from that in order to analyze the pressure signal and develop patterns which usually are used for chaotic systems. And actually, we do believe, although it is controversial, that a combustion system is chaotic. So you cannot, in principle, predict it through the normal fluid mechanics equations. So this is the case that I was showing in the video before of how this pattern is. And we have developed methods to actually process this and try to predict when the oscillation is going to start. We have developed 3 different methods, and the 2 lines indicate what is the forewarning period in order to react and do something so that it doesn't develop to the high frequency, high amplitude oscillations. And currently we can do that up to 1 second, and these are results from a commercial engine from a manufacturer, and you actually see the same phenomena that we observe in our combustor here in a commercial combustor, and actually the ability to predict the future. It is long enough, 1 second, to be able to react and control the operation. I switched to car engines, and I think that this is more related to the talk that we have afterwards. And I thought that I'm talking about combustion, and everybody has heard that everything is going to be electric. So I thought that I should reflect to that first before I present you what we are measuring. During my talk, there will be 2,300 new cars, which are as they are at this moment. And these cars are going to have a lifetime of 20 to 30 years because usually they move to different countries. They are used as taxis in different places around the world. And all these are going to be emitting whatever eventually the engine that currently exists. So the pressure that exists in a thermofluids researcher is to make the engines better yesterday, because already there are 2,300 out today as I talk, and these are not going to be as clean as they could have been. If I look at how many cars also there are around the world, there are more than 1 billion passenger cars currently, and about 300 million commercial cars. And if I look at how many electric cars exist, it's 1.2 million. So the emissions from all these cars, if I can manage to improve, say, by 0.5% of the efficiency, is going to modify significantly the contribution that transport has to the emissions, while the contribution of whatever the electric cars are going to do, without even considering how the electricity is generated, is not going to have a significant effect. And if you look at what the predictions are from the IEA, the suggestion is that only 10% electrification may contribute to transport by 2050. As a consequence of that, we want to look actually in combustion. So we do have a simulation of an internal combustion engine where you actually generate conditions that you do have inside the cylinder of the engine, inside a combustion bomb. Combustion bomb is not a good word to use, so it's combustion research unit. Especially in an email these days. You see that the assembly has to be to make sure that it is safe, because you have very high pressures and temperatures. You need to test the windows and ensure that eventually they work well. And effectively, you fill this up with an explosive mixture on purpose, and you ignite it. So you put a gas mixture. So you start, in this particular case, from around 15 bar. The blue line shows what happens after the explosion, that it goes up to 80, 85 bar. And then gradually this comes down. The temperature is the orange line, and it is more than 1,000 K. And at some point that you can select, you do inject liquid fuel, and you want to see how it evaporates or how it ignites. And I'll show you some videos so that you can see how things are. So this is atmospheric temperature and pressure. So you have a triple injection diesel fuel, and what you see is that now it doesn't evaporate. The liquid actually hits to the walls of the chamber, and effectively you generate a mist. If I do the same at 40 bar 1000 K, you have again 3 injections, and you see that actually most of the liquid is confined to the middle, and all around there is no liquid anymore because you have only vapor. And we can also quantify how much the vapor is by just shining a laser through the vapor part and using some fluorescence, and you see actually what is the vapor concentration away from the nozzle. You can see in the middle where the sprays are coming off. And we can also ignite the spray, and you can see actually the ignition occurring inside the chamber. You can see, sorry, I can see it on my, so you can see in the middle the liquid that is coming out. It has all evaporated, but the flame is all ignited away from the nozzle. And if I keep this running, you will see that eventually as I come at the end of the injection and the injection has stopped, the flame goes back to the nozzle, and actually the reaction gets completed, possibly. But it is important the fact that the flame is lifted, because that helps to reduce the emissions. And by seeing this, you do know that you have the chance to actually premix the fuel before you burn. And in order to verify that this actually happens, we had to quantify the mixing rate, and there is a very difficult quantity in thermofluids that I'm not going to attempt to explain, which is called the scalar dissipation rate. But eventually, when this value is red, which is high, you have very high mixing rate, and when you have high mixing rate, you cannot ignite the mixture anymore, and that is the reason from these measurements that eventually you can explain why the flame is lifted. And by controlling that, you can make the engine better. So this was in a combustion bomb, not inside an engine. I take you now inside an engine, which is optical, single cylinder, and I want just for you to see the similarity. This is 2 injections, one after the other, and then there is the ignition. The ignition is not a lifted off of flame in this particular case, and you will see why it is not in the next slide, where I change the injection pressure. So the injection pressure goes from 300 bar to 1,100 bar, and you see how the flame is completely different. Here you do have all the reaction happening more in the center, and it is more luminous because you have more soot, which actually, as you increase the injection pressure, is not there. And we can actually quantify after the end of the reaction by shining again another laser across. We can quantify how many particulates actually survive the reaction, which will find their way to the exhaust. And you see that, say, for the high injection pressure, you have a lot less than you had for the low injection pressure. So you can see that you can actually control the combustion process and improve it. In order to study the sprays that are important, we have to develop new techniques, and this is one which has also been patented, but it gives you laser, on a laser sheet, on a plane, you can measure simultaneously the droplet sizes and the velocities, which is based on an interferometric approach. And we have applied that in an unsteady automotive injector, gasoline direct injection. And you can see, if I focus at that corner, how the flow actually changes as I change the droplet size. So if I modify the droplet size, I can have a vertical structure, and the small droplets follow it, while the larger droplets will not do anything like that. So that modifies mixing. And if I look simultaneously, by using the same technique, how the vapor distribution looks like, you can see that I have regions, red regions is high vapor concentration. and other regions which are blue, where they don't have a lot. But the droplets which are and you know also the size, say here they are all concentrated in a cloud. You see that the vapor is higher there rather than around the droplets, which is not what you assume, because you always think that where the spray goes, that's where the vapor is. So it is not clear why, and we had to measure, and eventually we can quantify the behavior of the evaporation of the droplets, and you find that none of the droplets which exist in a spray, they evaporate as a single droplet, but they all evaporate as a cloud. Another problem that you have is that you want to look at how the atomization occurs, because that determines what droplet sizes you have. And if you are on holidays and you look at fountains, you realize that all the fountains, they look nice because they put the light from below, and you do the same by putting a laser beam through the nozzle, actually, and as a consequence, you use the liquid as an optical fiber, and you visualize what you have actually coming out of the nozzle. And this is a photograph of what you typically get, which is a shadowography. So the spray is the shadow. And you see that by using this optical connectivity technique, you actually see very detailed structure of the atomization, of the intact length close to the nozzle. And you can see also time-dependent behavior of the spray, which actually can be analyzed and explain how it works. And you can actually use this technique in a real diesel injector, and there is a difference between what you see from the sprays, which is what was on the videos that I showed earlier, and what you see actually when you put the light through the holes of the injector, and that gives you only the region where actually the liquid is intact and it hasn't broken up at all into droplets. Finally, the spray, when you inject in a gasoline direct injection, it hits usually a wall, and that is a source of particulates. And we want to be able to quantify what is the liquid film thickness that is formed on a particular surface. And as a consequence, we developed a new method which does not depend on what type of fuel you use. You can use any fuel. And basically, we develop a surface with a particular surface roughness in order to detect how much liquid fills the gaps. And as a consequence, we can measure what is the liquid film thickness below 10 microns. If you see the scale here, 7 microns is the maximum. And this is the liquid film that actually evaporates from this wall that you have. And in principle, you can use this technique in a real engine. We want also to be able to probe, again, in a real environment without having very large windows. So we want to be able to go through a hole. And this technique is actually using a single laser beam, is laser-induced breakdown spectroscopy, to generate locally plasma, say in a flame at this point. And from the emitted light from the plasma, which is what you observe here in a spectrum, you can actually find out how much is the air to fuel ratio locally. And this gives you a picture of how the plasma evolves in time and how the corresponding spectra, in order to be able to adjust the method and make sure that it works correctly by picking up the right time after you generate the pulse. We are developing also a new method in order to measure where the CO emissions are generated in a flame. As you go lean to reduce the emissions, you have higher CO emissions, and if you want to control them, you need to find out where they are generated. And as a consequence, you see here from the laser technique, we can see where CO is, and you can see where the flames actually have been. So the final part is that still there is development on engines, and I'm showing you just a video which actually is currently, Mazda announced the Sky Active engine last year, which actually is based on this concept. you see here that you had the spark which initiated the reaction and at this moment is evolving, while here there is no spark and actually you have a compression ignition and you see that the flame ignited and already it has been, the reaction is nearly complete. This condition gives you better efficiency and lower emissions relative to what you have from a normal spark ignition engine, and Mazda just announced that this is going to be their new engine. We have looked in this type of combustion and we have at least tried to understand how the temperature affects the ignition. I mentioned about sensors. We are currently working on an Innovate UK project, which was recently at the BBC Click, which develops sensors and models in order to be able to monitor what the emissions are from cars. And actually the purpose is to control the charge, but in principle you can use the same method to control also the engine itself. And finally, because I said that also you generate innovation, you need to use technology that appears from other backgrounds. So a plane optic imaging, and if you look at Wikipedia, you can see that what a plane optic camera is. But eventually a plane optic camera takes a photograph which is not clean. It looks like that. And then on the computer you process it and you get images at different planes of the field of view that you observed. So you see that this is focused and this is, and as you go to the other one, you just change the plane of focus and you can see what you have. Which means that I can take a single photograph and see a volume or what a flow does in space. So we want to use that for thermofluids and we want to be able to see the structure of a three-dimensional braking droplet. And we have developed our own camera and the software, and this is, there is some technology which can be patented, and this is currently being patented. So the end is, the lasers and the thermofluids can deliver, I think that I hope that I showed you, intellectually stimulating science, and also allows us to talk to our computational colleagues and try to collaborate. It has applicability in industrial and societal problems. For sure, at this moment, it is very interesting, related to combustion. It can innovate across different fields because whatever you do in combustion can be transferred elsewhere, and it helps also to generate IP. So I'll stop here. Thank you.
Yanis, thank you. All the speakers will be available in the tea break afterwards. I suggest we break now because we're slightly over time. So we'll reconvene at 5:30 for the main speaker of the event. So thank you for the time being, and there should be tea and refreshments outside. Thanks. It's my great pleasure to introduce Nick Molden this evening to give our keynote talk for the event. Nick's a very different profile to our previous speakers. Nick did a PPE degree at Oxford and has been interested in data analytics. He worked for a variety of companies before setting up his own company called Emissions Analytics. And Emissions Analytics, as you'll see from the title here, is basically what he's going to talk to us about. So, Nick, over to you.
Thank you very much, and thank you for inviting me. And that's a very sort of generous way of terming, a very different background to the previous speakers. You could also say largely unqualified to talk to an engineering audience such as yourself. So I trust you'll be gentle with me. But what I'm going to try and talk about this evening is the story of Dieselgate, and what it really is, where it really came from, what it was really about, and where it leaves us today. In my view, it's really quite different to the public perception, but it's nevertheless an issue which not just rumbles on, but in a way crescendos in terms of a subject of ongoing debate and profound economic significance, in my view. And I should say, there are plenty of facts in here based on our research, but overall, this is my personal opinion. My reasoned personal opinion based on the evidence. Ultimately, the history of Dieselgate hasn't finally been written yet, so I wanted to say that some things are still subject to opinion and interpretation. So, the original cause, where did it come from? And I think actually it's a very simple cause, and it originates in the United States, and it originates with the launch of full hybrid vehicles. What full hybrid vehicles did was set a new higher bar for the fuel efficiency of passenger cars. That then came at a time that Volkswagen as an organisation had aspirations to become the largest car manufacturer in the world. The technology that they'd very successfully developed here in Europe, the turbocharged diesel engine, was the tool of choice, they thought, to grow in the United States market. If they were unable to grow in the United States market, it would be very unlikely they could become sustainably the largest car manufacturer in the world. So diesel was the tool, but the bar was set by the hybrid vehicle. Had the bar been set by the traditional gasoline vehicle, in some senses it would have been a walk in the park, but it was set by hybrid vehicles. But the problem was that the US emissions regulations are really rather tough. We in Europe like to think we've been leading light in emissions regulation. As you'll find through this presentation, that's sadly not the case. In fact, the US has been very much the toughest, and by the role of both the EPA federally and the California Air Resources Board, in practice, the US regulations have been very tough. And that, in many ways, is why diesel technology was always difficult to take off, because, and the main problem with diesel engines is the engine-out nitrogen oxide emissions, but not just that are expensive to control, expensive to abate. And so that set up the temptation, in my view, of this major manufacturer who wanted to expand in the US in a market with very tough regulations, and it was hard to make these diesel engines comply, which were their speciality. It set up that temptation to find a way around the regulations rather than to actually genuinely comply. Just to give you an idea of the sort of magnitude of the difference, the chart here shows of the US vehicles we've tested, and which I'll talk a little bit more about later on. This gives you a measure of the difference between, in real-world operation, between the US gasoline vehicles over the last 5 years compared to the gasoline hybrid and plug-in hybrid vehicles. The plug-in hybrid, by the way, that's when it's operating in battery depleted mode, so that's effectively the sort of internal combustion engine only version. So you can see the significant difference in the efficiency and the reciprocal being the CO2 emissions of the hybrids. Had the bar been set at that sort of 380 grams per kilometre of CO2, the diesel would have been in a very strong position. It was that actually the bar had been set so much lower. So that was the original cause. VW were caught cheating, and we had all the lawsuits around that. But what actually the real consequence has been in the US market? In my view, very little. Yes, okay, I admit it, there have been about $30 billion of fines, and yes, there's been lots of remedial activity, and yes, a few executives have gone to jail. Okay, yeah, so it's not, but actually at a real macro level, for the automotive industry in the US, it's not actually changed so much. Diesel sales are still less than 3% of market share. And mostly those are still pickup trucks and premium passenger cars. But also, those diesels that are sold in the US are actually extremely low emitting for NOx. And this was true long, long before Dieselgate, apart from obviously the VW vehicles that were the cheap vehicles. Jaguar Land Rover selling in the US, BMW, Mercedes selling in the US. The sort of NOx emissions we're talking about is what's shown in this chart on the right-hand side. So we have the real-world NOx emissions, again from our test data on the roads in the US, expressed in grams per kilometre, so I can compare them with the European results. So the first bar is the average of all the European vehicles we've tested to date, so a mixture of Euro 5s and Euro 6s, averaging at about 650 milligrams per kilometre. In the US, all the diesel vehicles we've tested over the same period are actually averaging about 70 milligrams per kilometre. That was true before Dieselgate, it remains true after Dieselgate. And in fact, if you exclude, and I term this very carefully, if you exclude the Fiat Chrysler diesel vehicles currently under investigation by the EPA, on which I make no comment whatsoever, you actually get the even lower typical real-world emissions of about 30 milligrams per kilometre in the United States. So the fact that European vehicles had high NOx emissions and the US had low emissions was true before, it's true after. Not a lot has changed. And in fact, the US has relatively clean air. There was a research I saw the other week which ranked the US with the 5th cleanest air in the world. Now, you can get different rankings depending on which metric you choose, but the message is broadly clear. Because US have framed their regulations so much around trying to achieve compliance in the Los Angeles basin, that has actually set very tough rules, which has meant in many other cities, the air is really very clean. And the final thing in the US, well, actually, despite all the news flow around battery electric vehicles, it is more the hybrid vehicles of different stages which are gaining the market, the sales in the US, and there's a lot of innovation around that. So actually, not a lot has changed. But if we look towards Europe, a huge amount has changed. The consequences in Europe of Dieselgate were dramatic. Now actually, there's very little direct link between those two subjects. It just meant that Dieselgate led everyone to ask the obvious question, if VW are doing that in the US, what are they doing in Europe? And this just uncovered the fact that the average diesel vehicle in Europe was emitting 5 times the regulated level of NOx in real-world driving. Despite that, no one has been prosecuted in Europe, to my knowledge. Not a single certificate of conformity for a vehicle has been revoked by any type approval authority. So no one has actually broken any rules. So we've got these vehicles which on average are 5 times over the limit, yet it's legal. How can this be? Well, it's, in my view, a heady mixture, a confluence of, well, actually weakened regulation, an asymmetry of expertise, and commercial pressures. Now, what do I mean by that? Weakened regulation, the dynamic that seems to be in Europe is that Europe tends to have ambitions about strict emissions regulation, which then get progressively undermined by the nation states. And loopholes get engineered in through the negotiation and the political process in Europe. The interaction between Europe and the nation states seems to contrive to weaken regulation. Asymmetry of expertise, what I mean by that, if you look at the amount of experts within the European Commission versus the combined might of the manufacturers, there's an obvious asymmetry. And in my view, Europe doesn't take the really aggressive approach that US does by deliberately, for regulators, deliberately hiring expertise in from the industry to really know what goes on. So I think there's been more trust historically. And then the commercial pressures. Essentially, the desire, NOx is expensive to abate directly, and it can have, in certain circumstances, an effect on the fuel efficiency of the vehicle, so it has an effect on the consumer. So there's a number of commercial reasons why, if you can get away with it, you might try. Add to that, and again, where national governments have played a deleterious role, in my view, is within the old regulations, there was the provision for surveillance, just national governments having programs to check in real world. Most European countries have either never done any surveillance testing or stopped it. And it really does strike me as there was enough knowledge about what was going on, but there was a very strong political desire not to look because it got in the way of other political objectives. But net-net, and the commercial pressure in this is very strong, I think ultimately it worked out that it was cheaper for OEMs to spend time thinking about the loopholes in the regulations, to engineer to those loopholes, rather than actually abating the NOx emissions in the first place. And that is not inherently illegal activity. It was just a straight commercial calculation, in my opinion. So that's the origin, and in a way the immediate, where it, the debate immediately went. So just want to then quickly talk about us. And so where do we fit into it? How on earth can I say anything on this particular subject? So emissions analytics is a business I set up in 2011, privately owned. We operate internationally. We test and rate vehicles, and we publish that information. And because we're not part of any government or regulator or allied to any manufacturer, we're the ones creating the primary data, and so we have rights in that data to publish it. We're HQ'd here, but now have operations in Germany, the US, and latterly in Korea as well. And we do really one thing. We do on-road testing. Nothing else. We don't run laboratories. We focus entirely on real-world on-road testing. And I think I can claim to have the largest commercially available database of real-world emissions as a result. And we work with a wide range of people from the research side through to the commercial side, and importantly also the media side. What have we achieved? It's not all straightforward vehicles. We are occasionally found with aerial nomads in residential areas in bits of Britain, but it shows the flexibility of this equipment. In total, we've tested now about 2,000 passenger cars. Now that's not repeat tests on the same car, that is literally 2,000 different vehicles. We have a program of testing vans, heavy-duty commercial vehicles, tractors. We've got a growing program of non-road mobile machinery where we're working with King's College, so diggers, telehandlers, cranes, generators. If it burns fossil fuel, we're there testing it, including up and down the Thames. We're now doing some waterborne craft. This is the equipment we use, and very important to say is this is not something we've invented. This equipment existed before we started, but it was very much a quiet backwater. This equipment was actually a product of the last Dieselgate. So in the late 90s, there was the 7 heavy-duty truck engine manufacturers in the US did a similar cheat. It was a much cruder cheat than Volkswagen. I think it was based on if the bonnet of the truck was up, then it would switch to a cleaner mode because it guessed that meant that it was being tested. They were busted. The fine was $1 billion, which was a lot in the late 90s. And part of that money was put towards creating equipment like this that could be used to then check on manufacturers in the future. This is an emissions laboratory in a box which would sit very comfortably on about half of this desk. It uses the same measurement technologies you would find in an emissions laboratory. The difficult bit is packaging it small, the sample conditioning, how you deal with the ambient, protecting it from the ambient environment. It's a non-dispersive infrared for the carbon-based emissions, non-dispersive ultraviolet for the nitrogen emissions, a flame ionization detector for the hydrocarbons, a condensation particle counter to measure the particle number, all at 1 hertz with about plus or minus 2% repeatability. So very good precision. Put that together with a weather station for the ambient conditions, GPS for speed and altitude, the carbon balance method for fuel consumption measurement, and what you have is something which is very accurate, calibrated properly, very precise, but also you can measure a vehicle without modifying the vehicle at all. So the vehicle shouldn't know that it's being tested, and that's very important in avoiding cheats. So with a fuel flow meter or other interventions on the vehicle, it is much easier to spot if you're being tested. Now this is what it looks like, and I put this vehicle up because actually it almost tells the whole story in one. So this is a 4.2 litre Porsche Panamera diesel 4-wheel drive. Firstly, it shows it's a quad exhaust. You can put all our equipment on it, test it without any modification. It's one of the cleanest diesel vehicles on the road. It very comfortably meets the limit. Yet Porsche announced last week that it's discontinuing it. So in a way, I could pack up and go home. That is the story told, that we're cars which are clean and compliant and were popular are being discontinued for a variety of optical, commercial reasons in the current environment. But that's one we've genuinely tested, had very low emissions, and I can take all that equipment off, hand it back to the owner, unmodified, and so it's given us ability to test vehicles from a wide variety of sources. So that's what we do. So we get lots of vehicles and test them. So back to the story. So then people started asking questions about Europe and what was going on. And by that time, we had a lot of data. And this helped propagate the story, if you like, or understand the story and inform what was really going on. So this chart here plots all the diesel vehicles we've tested until last year. And the color coding, so time is on the horizontal, the real world NOx emissions are on the vertical. And the color coding is the orange is the latest Euro 6 vehicles, blue is Euro 5, which came on sale in 2009, and the grey ones are anything before that, a mixture of Euro 3 and Euro 4. On average, both the Euro 5 and the Euro 6 are about 5 times over their respected regulated limits, which are marked by the horizontal lines. But the absolutely key thing here is you see the spread in the results. So this shows that if you're trying to work out what the real world emissions of a diesel vehicle is, the Euro label that you get gives you very little information at all. The whole system is being debased by the optimization around the official system. Because what you can quite clearly see, so the dirtiest of the Euro 6 diesels are 6 to 7 times worse than the cleanest Euro 5. And 3 times worse even than the cleanest Euro 3 and 4. So you could have a vehicle which is 15 years old and substantially cleaner than one you could buy new today. And just to give a very concrete example, the one down here at 2005, the grey blob, which is just under 400 milligrams per kilometre, is a very high-selling one from the Volkswagen Group. And you have the orange one top right is a very high-selling model made in the UK. So you could find that you sold your 12-year-old Euro 4 vehicle and bought brand new Euro 6 diesel, you thought you were doing the right thing, and actually you quadrupled your real-world NOx emissions. And this is a problem for government as well, with scrappage schemes. Scrappage schemes are one of those things, like, it sounds like it must be a good idea. But if it was my taxpayers' money paying someone to make the swap from that one to that one, you will have spent a lot of taxpayers' money making the problem worse. So that is the degree of the problem from a policy point of view that we're left with. Essentially, some 20-year-old cars are cleaner than brand new ones, and it's all legal. In my mind, it is more akin in a sense to maybe a PPI mis-selling scandal. What is in the brochure, in the showroom, is not giving you the right information. It's what people, the manufacturers say, and also they're legally obliged to put this information out there. So on one level, you can't blame them. But it is nevertheless leading people to make the wrong decisions. Then it gets worse. So this is the same data over time, but I've changed the vertical axis to the exceedance factor. This is my term, and it's just simply the ratio between our real-world emissions and the regulated level. And this is to illustrate. It was roughly at 4 to 5 times over the years. There was a brief moment of light in 2014 where the early Euro 6s looked like they were going to be a lot better, 2 or 3 times. This turned out to be the best placed manufacturers bringing their good, relatively clean diesels to market early in the Euro 6 cycle, but then as soon as everyone else followed, it brought it back to 4 to 5 times. But then what happened in late 2016, 2017, in the run-up to the new real driving emissions regulations coming in last September, the temptation to game this introduction became overwhelming, in my view. Essentially, all new types of vehicle now have to meet the new tougher standards. But if you were type approved just before the introduction, your vehicles don't have to comply until September 2019. So if you sneak it in just before the deadline, you buy yourself 2 extra years to make your diesel vehicle genuinely clean. So, not surprisingly, in my view, the manufacturers with dirtier diesel models, which they needed more time to fix, got as many into the market as possible before the introduction of RDE. Real driving emissions, the new regulation. And you can see that by the rising average exceedance factor, which went from the long-term average of about 4 to 5 up to 6 to 7 times. Now it's falling as the new RDE cars come onto the market. But the problem is that those vehicles can still be on sale as new vehicles through to August 2019. And then you add to that the age of that vehicle, so they're likely to stay on the road for 15 years, maybe 20 years. And it comes back to the presentation just before the break as well. This, in terms of the speed with which these vehicles can actually make any difference to air quality, is determined by these sort of factors. And the fact that the market is stuffed full of dirty diesels at the moment makes that job so much harder. Now, you may ask, actually, how can this possibly be from an engineering point of view? How can it be that a vehicle, in fact, the worst ones are 18 or 20 times over the limit, yet they're still legal on the certification test? Well, there are 2 strategies which we believe are widely used, which can explain it. Thermal management strategy is quite simply the test in the laboratory happens at a certain designated temperature range, and there's a provision in the regulations to switch off or down the after-treatment system to, quote, protect the engine in colder or more extreme conditions. So some manufacturers have done just that at 17 degrees Celsius. Now, I don't think you'd find an engineer in the land who would say that the engine needed protecting at 17 degrees Celsius. This was intended to protect at -5 or worse. But nevertheless, it was a loophole that was legally able to be used. And a hot restart strategy is simply that the official test starts from a cold start. So if the engine is warm, you know you're not being tested. Hey presto, you can switch to a dirtier mode. Okay, so that's the tactics. So this is what everyone now thinks a diesel engine is like. We know that we're in breach. A lot of locations in UK and Europe are in breach, not just of the legal limits, but they're not in line with the WHO guidelines, which are about half the levels in terms of ambient concentration. The research into the health effects is growing. Diesel technology is being blamed, and Client Earth and the Deutsche Umwelthilfe are taking governments repeatedly to court for breaking their own laws. I mean, that's essentially what it is. I mean, they're just trying to get the governments to abide by their own laws. But this leads to a very charged political situation. So what's likely to happen, and what does the data tell us is probably the optimal solution? So the first round effects, that, in my view, of Dieselgate, the first round effect of consequences is there's been a big loss of confidence in the official data. And a loss of confidence in manufacturers as well. It's left consumers not knowing what the right thing to do is. I mean, people don't have a lot of patience for talk of NOx emissions, but they do have a fuzzier sense of wanting to do the right thing. They don't want to buy a car that's going to poison their children. Okay, most people probably don't know the difference between CO2 and NOx when it comes to it, and probably don't have the time. And why should they? But it has led to a paralysis of a form of not knowing what the right thing to do is. Similarly, fleets, when expressed through fleets, it's more a corporate reputation concern. This is all leading, as you know from the news, to the sales of diesel cars in most, not all, but most European countries is falling. So far, so simple. But then there's a whole bunch of second-round effects that have been set off. Firstly is the second-hand values of diesel vehicles has started to fall. As a result, the sales of used diesels have started to go up. They're a bargain. So, actually, so suddenly these dirty old diesel vehicles have become an attractive product for people. The sales of gasoline vehicles is a lot more robust than diesel vehicles. So, car for car, that like for like, that leads to approximately a 16% increase in CO2 emissions. Okay, that's not great either. We all think that technology neutrality is a good idea. What actually is happening is governments are increasingly having to introduce more and more technology-specific policies to neutralise the technology-specific policies of the EU. Essentially, the EU regulations flatter diesels. Diesels have a higher NOx certification limit, so that's making diesel's life easier. And then you've got the UK government introducing extra VED on diesels to try and neutralise that effect. So you've got a very bizarre clash of policy there. And then, and I'm probably going to get really slated for this one, OEMs, in my view, are happily receiving subsidies to develop EVs, despite them having no rapid effect on air quality. And what I mean by that, it's through the super credit system in fleet average CO2, it's through helping develop infrastructure, a whole range of, not explicit subsidies, but indirect subsidies. And manufacturers are quite happy because anything to do with EVs helps reputationally with the background of distrust. Now, okay, that is highly simplifying it, and I say that to be slightly provocative, but I do think at the moment there is a happy equilibrium between of everyone wanting to be seen to be doing something really active on the EV side, even though it will have zero benefit to air quality in the near term. What is happening in the near term, though, is cities planning to ban or restrict diesels in different ways, which has got national governments agitated because what they don't want is, well, they don't really want cities to ban diesels at all, but they certainly don't want cities to ban diesels in lots of different ways. Because if different cities had different restrictions, that would create immense confusion for consumers. So they're trying to standardise these bans. And then because the residual values are falling, owners are suffering capital losses. Cars that they bought in good faith, they're suffering capital losses. Now it becomes clear what is happening. And the danger is that industrial and employment effects will follow. So that's what's actually happening, in my view. So what's the reality of it? How much is that actually justified and how much of it is not justified? Well, this is the same data as I showed on the slide slightly earlier, but with added gasoline information. So again, real-world NOx on the vertical, time on the horizontal. These are all vehicles, again, we've tested. The grey is the bold grey line is the average NOx emissions of the diesel vehicles, but the long dotted one is the cleanest 10% of diesels, and the fine dotted one is the cleanest 5% of diesels. So, and the orange is all the gasolines we've tested. So the cleanest 5% of gasolines on the market today, even before the new tighter regulations, this is all pre-RDE, those 5% cleanest diesels are as clean for NOx emissions as gasoline. And in fact, if we look at it a slightly different way, if we look at the dirtiest 10% of gasoline compared to the cleanest 10% of diesel, actually those dirtiest 10% of gasoline emit 84% more NOx than the cleanest 10% of diesels. So taking two extreme groups, but to illustrate the point. And don't forget, the average CO2 emissions of the diesels for gasoline is 16% higher than for diesels. And the thing which is being slightly overlooked with all the focus on NOx at the moment is the particle number emissions. Most gasolines have higher ultrafine particle emissions than a modern diesel with a particle filter. Not in every case, and the levels do vary hugely. And direct injection gasoline, some direct injection gasolines suffer from the problem particularly, but generally a diesel with a good filter will have very low levels of particulates as well. There is another a terrible irony in this as well. So while thinking about NOx, what about that CO2? Well, the whole push towards diesels was for CO2 reduction. I mean, the policy of CO2 reduction was, very strong, initiated 10, 15 years ago. And the old NEDC certification system has led us all to think that we've been year on year reducing CO2 emissions. It turns out that's not true. This is a graph of, over time, the real-world CO2 emissions in grams per kilometre. The grey line is European diesels, yellow is European gasoline, and the red is US gasoline. Over time, they have been completely flat. There's been no reduction in real-world CO2 emissions at all. At an aggregate level, though, there has, due to a mix effect. So the shift towards the dieselization has led to an aggregate reduction in CO2 emissions. But what it shows is if we go into a phase of reversing the process of dieselization, the baseline scenario has to be that the CO2 emissions will go up. This apparent big improvement that we've had is illusory. It's also illusory in the US as well. I mean, you can see, they're all three are almost completely flat. Where there has been some improvement, it has generally been by downsizing. But in Europe, downsizing has gone too far. And it's got into the zone, actually, some very small downsized vehicles have actually had worse CO2 emissions in real-world driving than slightly larger engines. So that's gone too far. So actually, there's an opportunity in reversing that trend of over-downsizing, and we can actually get a CO2 benefit. But the important point, it's a mix effect on the powertrain types, not a like-for-like improvement in real CO2 emissions. So what's going to happen? I think the policy opportunity, it's really politically difficult. What I think is logical, looking at the data, is, well, actually, pre-Euro 5 diesels have an Achilles heel which is high particulates for most of them, because most didn't have a filter on them. So there's good reason to want to restrict those off the road as soon as possible. So you're then left with the Euro 5 and Euro 6 diesels. And the problem is, if you do it based on the Euro standards, you get a very, very blunt instrument. You really want to be able to discriminate on the basis of the real-world emissions. So, and by our calculations, if you hypothetically restricted 90% of the Euro 5 ones and about 50% of the Euro 6 ones, you would bring about an 87% reduction in tailpipe NOx emissions. But if you did it on the basis of just the Euro stages, you would not get anything like that degree of effect. There's also there's a benefit in trying to incentivize manufacturers to go beyond the minimum. So rather than just about meeting the regulations, to go well below. And we know from the testing in the US that diesels are, and you saw from the first chart, that diesels can achieve 20, 30 milligrams, even less. So we don't want just minimum compliance. Any retrofitting system, which is being talked about a lot in Germany, needs to be validated. We must have, if it's going to happen, it must prove to work and be robust over time. And as I illustrated earlier, any scrappage scheme needs to be very, very carefully targeted. To help solve the problem, we've taken all our data and we've created free ratings. If you go to equaindex.com, you can use and see all our results. And that's what the sticker for NOx emissions looks like. And just to make the point, the distribution on the A to H scale of the Euro 6 diesels is the bottom left there, where shows is of legal cars to sell, there are A's and there are H's. There are 20 models which get our A rating, which means 80 milligrams per kilometre or less. But at the same time, on the road, there are vehicles which are emitting 1,200 milligrams and above, all on the forecourt today. We also publish off the same data. It's very important to see at the same time, particularly the CO2 emissions, but also the fuel economy, because that's how you can get consumers interested in using this data. And so to try and wrap up, this is my way of trying to bring together the technical with the commercial and looking at the main, in very simple terms, the main powertrain types and 4 key characteristics of them, from the efficiency, the depreciation and in-use emissions. The plug-in hybrids and EVs, the main problem with them is that they're too expensive. They lose their value too fast. Now, I don't want to, because I could speak for a long time about that, so I'm not going to, but that is what constrains their ability to make any big shift in the market in the short term. So what we're left with is diesel, gasoline, and hybrids. And what you can see, we know that diesels had better fuel efficiency than gasolines. That's why they were interesting in the first place, and lower CO2 emissions. But it's the top right-hand cell which I want you to focus on. The question of whether diesels have good or bad in-use emissions is critical. If that is a red cell and diesels are seen to be bad, it's actually the gasoline hybrid is a dominant technology. If that cell were green, then it's a pretty even fight between gasoline, hybrid and diesel. So this marketplace, in my view, turns on whether diesels can prove themselves, to whether they are clean and whether they can communicate credibly that they are clean. If we had to switch back to straight gasoline, there would be the problem, as we know, of higher fuel bills and higher CO2 emissions. So at least if there is going to be a swing away from diesel, it must be towards gasoline hybrids, otherwise we'll store up a very large CO2 problem. And to make it concrete, this is the sort of choice that you would have as a consumer. I've put here a typical, on sale today, an example of one of the cleaner diesels, the Passat 1.6 litre. A very good example of a full hybrid, the Hyundai Ioniq, gasoline hybrid. And then I put up the Tesla 3 as well. We've tested it independently on the same route and converted the electricity consumption to an equivalent MPG, which I know is not a perfect way of doing it on relative energy content, but bear with me. What this says is, essentially, actually, between the diesel and the hybrid, it's a pretty close thing. They're pretty evenly matched, so long as the diesel for Equa AQ is clean. They're good substitutes, and they're at similar price points. Compared to the Tesla, obviously it has no tailpipe emissions, and it's about twice as efficient. But it's also 50% more expensive. And so that in a nutshell is where we've got to today. That is the choice that we face. But the diesel shouldn't be counted out so long as that Equa AQ, the NOx rating, is a good one. So finally then, what is the optimal response? My view is that there is, from an engineering reality point of view and what we can see from the clean diesels, diesel could well endure for passenger cars, this is. For heavy duty, I think diesel will endure for a lot longer. But for passenger cars, it seems to me the optimal outcome would be for diesels to stay in the market in a significant way for at least a sort of 10-year period, so long as there is a discrimination between the clean and dirty ones. This will allow a more progressive transition to a variety of different levels of hybridization, from mild 48-volt hybrids through to plug-ins and other technology that may not even be in the market yet, which will probably sustain us well for a further 10 to 20 years. Ultimately, this all comes up against the requirement to reduce CO2, and there is a limit to how much you will be able to reduce the CO2 from anything with an internal combustion engine, and that is ultimately the driver of fuller electrification. In my view, electrification is nothing to do with air quality improvement. We can achieve the air quality requirements, even the WHO guidelines, with variants on the internal combustion engine, just done properly and enforced properly. But it's the CO2 which is driving that deeper electrification. The benefit of doing this in a more rational, data-informed way is it gives the market more time to adjust. And in doing so, it then falls in with people's natural replacement cycle, both private individuals and fleets. And so it helps minimize and smooth out the economic and social effects. And that is really important, and is the opposite of, say, diesels having a blanket ban in cities across Europe. Plus also, it does have the first point, if we can achieve some form of discrimination within diesel vehicles, it does mean, in practice, more of the cost will fall on the manufacturers who did produce the dirtier diesel vehicles, because they will suffer some market detriment. And, you know, it's not for me, despite my qualifications as in philosophy, I'm not here to make ethical judgments, but it does seem a little odd that vehicles can be 18, 20 times over the limit and be legal. You know, that it doesn't sound right. And so possibly, if there is some degree of alignment of the cost in solving the situation with those who are the greater contributors, maybe there's an element of fairness, rather than the consumers who spend their own money buying vehicles in good faith based on the official information. So I think, and I think there is clearly at the moment the rampant anti-diesel narrative based on often very partial information, put together with there is undoubtedly a battery electric vehicle evangelism going on. It's obscuring what the right policy response is. The right policy response should be fact-based. To help this, I've personally sort of co-founded a not-for-profit campaign organisation called AIR, Allow Independent Road Testing. The idea of trying to, as an umbrella for any like-minded people who want a factual, informed debate, to make sure we don't go down some irreversible, suboptimal policy decision, and to bring the facts to bear and try and get us to a pragmatic response. So that's, I think, I've taken you through where it all came from and where we are today. And this, I think, is, ideally, the consequences should be this optimal response. I fear that politicians may not take a strong enough stand to make sure we do go down that road, but I will continue testing vehicles and making this data available to try, because I think everyone in the room here would probably share the view that we should be as fact-based as possible and as rational in our decisions, and particularly over a subject which affects us all and has major impact for industry and employment across Europe and wider. So on that note, I'll finish. It does leave us a little bit of time for questions. So thank you very, very much for listening.
Thank you very much for that.
was interested in all your data points. I don't know what the error bars around those data points would be, and if you tested the same car 10, 20 times, could that same model of car be as clean and as dirty as what you said? And if so, why?
No, that's data is not on the side. I could show it to you. If you test the same vehicle multiple times, you will get actually a very consistent, as long as you test it in the same conditions. So if you tested one with a cold start and one with a hot start, you could, from the same car, you can get dramatically different results, undoubtedly. Our testing, it's always in from a warm start with ambient conditions in a certain range on the same route, same driver. Our philosophy is trying to get the maximum comparability between different tests, and in that case the error bars are small. But I completely accept if you have a different experiment, which is to try and see how different you can get the results from the same car, yes, you could get a much, much greater spread. But that's not the dimension I'm trying to illustrate here.
I've got two questions. One, if you looked at battery vehicles, they usually need to be charged, and if you use fossil fuels to generate the electricity of that, that will produce NOx and CO2. So how have you done, do you know of studies that have looked at how then the vehicles compare with the current mix of fossil fuels you power your battery? And the other one is, how do you trade NOx versus CO2? What's the equation to, because they're two different pollutants, very hard to...
Trade them for what purpose?
Well, they're both pollutants, so
Mm-hmm.
you can't put them equal. Can you put them equal?
No, you can't.
Supply, on a population basis?
I think that's a very dangerous route to. I mean, that's why we publish the ratings separately. There's a CO2 rating and there's a NOx rating. Other people do calculate combined eco ratings, and I think that's a very dangerous route to go, because that's essentially just an expression of your personal value judgment of the importance of those two, whether rising sea levels or poisoning people in urban areas is more important, and that's an ethical decision I'd rather not make. So to your first question, though. There's not direct research we've done as yet. I mean, the research I've seen is you are still, from an emissions point of view, better off with the battery electric vehicle because of the efficiency of creating the electricity from some central power station and the downstream efficiency of the electric motor driving the vehicle. But you do have the weight of the battery is a very big element in that you're carrying around a very large weight in that vehicle, which works against the efficiency of the electric motor. You could, but again, you get into then it's a highly sensitive function to your assumptions on trip length, and you can get hugely different results. Whether if you do lots of small trips with cold start, you'll get one answer. If you do smaller number of long trips, all warm start, you'll get a completely different answer. So you can't generalise the answer to your questions.
Can you say something? You made a very good point that the cleanest diesels are really very good. Can you say something about the technology that's used to get at that? Is that just urea injection, or is there more to it?
Urea injection, the selective catalytic reduction, that is the heart of the systems. But increasingly, and particularly in the US, the clever combinations of that with lean NOx traps, and also the particle filters, and using the waste heat from the engine and packaging it all in a very clever way. So the SCR deals with the sort of high volumes of NOx at higher engine load. The lean NOx trap cleans up the cold start phase, and you use the waste heat to help heat the SCR up as quickly and as efficiently as possible. So there's been a lot of work in designing these very clever combinations of after-treatment system. But I mean, SCR is the core of it. Anyone who's tried to get away without an SCR, it's a risky game. It's possible, but you don't leave yourself a lot of margin for error.
Can I share with you my experiences of being Chief Scientific Advisor at the Department of Transport? The Department of Transport is populated by people with PPE degrees in Oxford. I say that without any bias, but they're and you gave an excellent
do not know how to answer. So, but what I will say is that, in a way, you need a system which is well structured to guard against whichever flavour of Oxford degree populates the Department of Transport. So you need a robust policy, and that's what actually the US system is rather good. Because not only do you have creative competition between the EPA and CARB, which is very helpful, but you also have essentially secret surveillance work that the EPA does. So they go and get about 125 vehicles a year from real Americans, pay them to borrow their car, and they do testing. They don't say when they're going to do it to the manufacturers or exactly how they're going to test it, but is there sort of surveillance. So it adds jeopardy to the situation, and they have big fines as well. So it introduces an uncertainty, and that if there is a problem, it gets found soon. And that's really, if we go back 10 years, that's essentially where the US and Europe diverged, in my view. Both regions saw that there was beginning to be a gap between reality and the official figures. The US made their system much tougher, and it nipped the problem in the bud. Europe did not, and it allowed that gap to grow. And so I think it is about creating a system which has sort of levels of redundancy in it. That means it's sort of insulated from the latest policy fad or certain influential, individuals. That I think is that's what we should learn from this. And actually RDE, the real driving emissions regulations, in a way I think it is a shame that we didn't just copy the American system, because it's well proven. But not doing that, actually RDE has many strengths about it, particularly the in-service surveillance, which actually is very strict.
I think one of the things I would say is, looking at your bullet point 3, pending electrification 20 plus years, one of the things the government hasn't realised, and haven't really sunk in properly, we've got an energy crisis in the UK in terms of baseload electricity. So our nuclear power stations will be decommissioned over the next decade. It's going to leave a 20% gap in our baseload electricity. Even the distribution network itself can't handle that. Absolutely no way that's going to happen in 20 years, because we haven't got that. The baseload electricity, we haven't got the distribution network. The government has gone through essentially reactive policy in getting rid of diesels prematurely. I think the optimal response is not going to happen. Can't see it.
Well, in defence of PPEists, that's why I put a plus sign after 20 years. I hesitate only that my knowledge of EVs are not as deep as my knowledge of the internal combustion engine, and obviously the different pattern of emissions creation and the power requirement. That's not my absolute expert, so I check myself before making stronger claims. What you say is very rational. I think one thing that might happen, in a way, the get out of jail free card potentially here is mild hybridization. So you could essentially, I think it's quite possible that most models will be this 48-volt mild hybrid system could be added on, which is relatively inexpensive. It would allow OEMs to claim that the car is a hybrid, which it is in some sense, and would escape most of the bans. Now that's a bit cynical, but the government announced ban here of banning pure internal combustion engines by 2040 is not a properly defined statement. And I get different interpretations from different officials at the DFT as to what it means. The politics part of me thinks it was deliberately ambiguous. But the most common explanation of it is that it affects only non-hybridized. So if you can quite simply and cheaply hybridize every internal combustion engine, actually all of those escape the ban, and we carry on with a largely internal combustion engine powered fleet for decades to come. Now maybe that's a bit cynical, but I counter ambiguity with cynicism.
Just to counter this point,
said on Channel 4 News, the car manufacturers told us that they were complying, and we believed it. So it had nothing to do with PPE at all. The industry knew perfectly well what was going on, and the government could have known quite easily what was going on as well. But they ignored the problem. Just to go more into what you were saying, Nick, about American cars and so on, you were talking about the premium sector, and you had your picture of the Porsche Panamera, which is a premium sector car. It's very expensive to make clean diesels. And in Europe, we have a lot of cheap, small diesel cars, and that's the problem. If we want to make them clean, it will be very expensive. And your final point about mild hybrids is exactly right. We can make a very cheap solution with mild gasoline hybrids, which will do what we want. They won't run electrically in cities, and that's the problem, whereas full hybrids will run electrically in cities, and cities are going to really tighten up. London's going to tighten up by mile, and it will say you have to run electrically in cities, and that is going to be the issue. So I can quite see where you're coming from there, but in practice it will be a very expensive option to clean up diesels.
Well, I mean, I agree with a lot of what you say. I think there is still an open question about whether mid-market diesels can be made clean. And that the small diesels are largely being abandoned anyway because there's just no margin in it. Can a mid-market diesel be economically and effectively cleaned up? That I think is still a live question. And two pieces of evidence I will put in support of my position is, firstly, I mean, we tested one of the more expensive models from a very mass market manufacturer just last week and came up with about 30 milligrams per kilometre of NOx. And also the other, and one of the massive ironies in these things is actually Volkswagen, if you take all the Euro 6, the average performance on NOx of Euro 6 vehicles of any manufacturer, and Volkswagen is the cleanest. The 2-litre and the 1.6-litre engines they're not the cleanest in the market, but the way it's propagated across their range, on average, they are actually the cleanest in real-world operation. And many of those are pretty mass-market vehicles. So I still think it's still to fight for in that territory, even without any hybridization. Having said that, I still think it'll be advantageous to put the hybridization on as well for the CO2 point.
One last question, Frank?
Yeah. You haven't mentioned any alternative fuels. There are alternatives to both petrol and diesel that you could devise. That's out of scope of what you've done. Has there been any thought?
We have tested quite a few alternative fuels of different varieties. I mean, from sort of E10, GTL, and some, in fact, quite a few. The issue is that they tend to make small differences, or they can have a benefit in one dimension and a disbenefit in another dimension. The problem with these European diesels, if you're 5 times over the limit, and that's the average vehicle, could an alternative fuel get down from 400 milligrams to 80 milligrams? I'm sure that there's no alternative fuel that could achieve that. I think alternative fuels is largely about CO2 reduction, and I think it will be one tactic amongst many to eke out that progressive reduction in CO2, which is so hard and so expensive. If it can lead to a 2% reduction in CO2 that you can propagate through the fleet relatively logistically easy, then actually 2% across the fleet is definitely worth having. So I think that's where the fuel can potentially act, but what you need to have is a high confidence that all the different vehicles of different shapes and sizes will react in a similar way. There's no point if it delivers a benefit in certain types and a disbenefit in others. So you need to be able to evidence that uniformity of benefit across the fleet before you can confidently roll it out.
Okay, I think we're running out of time here, so we ought to let Nick get a
Okay.
drink at this point. And on the topic of philosophy, the opportunity to tell my favourite story from the weekend, which is that if a philosophy lecturer goes on strike and all the students sleep through the hour anyway. Did it happen? So Nick, thank you very much indeed for a very entertaining and very informative talk. And please join me in thanking Nick again.